All right, so jumping pretty much right into it, today's plan is to finish the chapter 4 PowerPoint that we started last week, and then to start and finish chapter 4 PowerPoint part 3 on the end of chapter 4 on counting, and then possibly start chapter 5. I didn't quite have enough time last week to get that last supplement posted, so I'm going to post that either today or tomorrow. So had some administrative things pop up at the end of the week that I needed to take care of, and just kind of ran out of time for that. But I will send out an announcement when I get that posted in the next day or so. Also, the midterm exam is coming up in the next couple of weeks. So 2 weeks from now will be the beginning of the midterm exam window. I'll post some more details about this on Blackboard when we get closer, but kind of in short, the exam will be available for a 1 week window from Monday at 9 a.m. through Sunday at 11:59 p.m. And you can take it anytime during that week. So I think that's the week of the 18th. You can check the course schedule just to be 100% certain. But I'll have the sample midterm exam up. It'll be quite similar to the actual midterm exam. So you can use that. I kind of recommend using that as if it were the actual exam. Sit down, take it as if it were the exam, with the same resources and everything that you'll have, and see how you do in the midterm exam. If you're happy with your performance, then you're probably pretty well set for the midterm. If you're, not so happy with a particular topic or something like that, if you struggled on a certain topic or a certain question, maybe go back, review that topic before the midterm exam. So I recommend taking the sample exam as kind of a self-assessment rather than, say, looking at the sample exam and treating it something more like a homework or something like that, where you're kind of going back and forth between the midterm exam problems and the textbook and other resources. Or some students will just like take problem 1 of the midterm exam and like drill it 10 times, and then problem 2 and drill it 10 times. I don't really recommend that strategy either. So I don't recommend, studying to the exam so much as I recommend using the midterm exam as a self-assessment of how well you know the different material. Okay, so with that being said, we'll jump back into the PowerPoint. And last time we mentioned we have an addition rule. The addition rule is concerned with whether 2 events are mutually exclusive, and it deals with events that are connected with or. So our addition rule said if our events are mutually exclusive, probability of A or B is probability of A plus probability of B. And if not, if not mutually exclusive, then we have to have this slightly less nice formula. We mentioned with the multiplication rule, when we have 2 events connected with and, probability of A and B is probability of A times probability of B if the 2 events are independent, if knowing that one of the events occurred doesn't affect the likelihood that the other occurs. But if the events are not independent, if they're dependent events, we need the slightly more general, not quite as pretty formula, probability of A times probability of B given A. Remember, this slash is pronounced given, and it represents a conditional probability. Again, we talked a bit more about that last time. And where we left off last time was discussing this manufacturing plant that has Some machines producing widgets. Again, a widget is just kind of an arbitrary thing. It's like how we use X in math is just like a variable that can represent any number. A widget is just something that's being produced. So we run a manufacturing plant producing widgets. There are 4 machines producing them at the same rate. For a properly functioning machine, the probability of a bad widget is 4%. And for a malfunctioning machine, well, it produces only bad widgets. And we want to find the probability that a randomly selected widget is bad. So these 4 machines produce their widgets, they get mixed together, put in a warehouse or something. We pull one off the shelves, send it to a customer. What's the probability that it's bad? And as we mentioned last time, we can kind of think of this graphically, that our widgets could have, or our widget, the one that we choose, could have come from a properly functioning machine, or it could have come from a malfunctioning machine. Of the ones that come from a properly functioning machine, I could get a good one or a bad one. And same, at least in theory, from the malfunctioning machine, could get a good or a bad widget. And we want to find the overall probability of getting a bad widget. And as we mentioned last time, the event getting a bad widget, well, there are 2 ways that I could do that. I could get a widget that's bad and from a properly functioning machine, or I could get a widget that's bad and from a malfunctioning machine. If I look at the probability of these occurring, I notice that I have probability of A or B, and these are clearly mutually exclusive. A specific widget could not simultaneously have come from a malfunctioning machine and a properly functioning machine. This is a partition of the bad widgets into mutually exclusive categories. So we can use our addition rule for mutually exclusive events. And now the question is, what are each of these probabilities? Probability of getting a widget that is a bad widget and is from a properly functioning machine. What's the other probability? Probability of getting a widget that is a bad widget and is from a malfunctioning machine. And that's what I have on this slide. So in this case, when I write from, that means the same as and. So there are 2 ways I can get a bad widget: bad and properly functioning, or bad and malfunctioning. Probability of bad and properly functioning. Now, again, these are not independent events, right? If I get a widget from a properly functioning machine, it's probably going to be a good widget. If I get one from a malfunctioning machine, it's certainly going to be a bad widget. So I need to use my multiplication rule for dependent events. Probability of bad widget and properly functioning machine is probability of properly functioning machine times probability of bad given properly functioning machine. 3 out of 4 of my machines that are producing widgets at equal rates are properly functioning. So the probability that a randomly chosen widget that I choose will be from a properly functioning machine is 3 out of 4. The probability that I get a bad widget, given that I picked one that's from a properly functioning machine, from the problem statement is 4%. 3/4 of 4% is 3%. So this bit here is 3%. And similarly with the bad widget from the malfunctioning machine, 1 out of 4 of the machines is malfunctioning. But given that I choose a widget from a malfunctioning machine, the probability it's bad is 100%. This gives me 25% for this second probability. And adding the two together gives me the total probability of a bad widget of 28%. Now, one thing to note is let's just take this, for example, probability of bad widget and properly functioning machine. I suppose I could have split this up as probability of bad widget times probability of properly functioning machine given bad widget, right? That would also be in line with my multiplication rule for dependent events. It's a question of which one of these I label A and which one I label B. If I label them A and B like this, then I end up with this result. If I label them the other way, the and operator or the and conjunction is commutative, right? It's A and B is the same as B and A. If we switch the order around, it doesn't matter. So I could have just as well labeled this A and this B. So I always have two ways of breaking up an and like this. And note that these are not exactly the same, right? With an or, the or conjunction is also commutative, but nothing changes, right? If I swap the roles of A and B, plus is also commutative. I just get probability of B plus probability of A. Or I might swap A and B to be B and A, but everything is symmetric. But here, not everything is symmetric. The choice of which one I condition on is a choice that I have to make. Why did I choose this option and not that option when I chose how to split up this this compound event with the multiplication rule? Well, I look at the probabilities that I need to be able to find later on. Well, first off, I'm trying to find probability of bad widget. Do I really want to have probability of bad widget popping up on the right-hand side? Probably not, because that's the thing that I'm looking for. I mean, maybe there's some kind of strange case where you'd want to be able to like write this out and then like solve for probability of bad widget or something, but that seems unlikely. And then what about this one? Do I know something about the likelihood of a widget having come from a properly functioning machine, given that I know it's a bad widget? So I pull one off the shelf, I test it, I find out it's a bad widget. Do I know in that circumstance the probability that it came from a properly functioning machine? Well, no, I'm not given that information anywhere. That's not to say it would be impossible to figure it out. Maybe I could figure it out based on the information I'm given, but it's certainly not readily available. So I really don't have either of these pieces of information. The overall probability of a bad widget, that's what I'm looking for in the first place. Or this piece of information, given that it's a bad widget, what's the probability that it came from a properly functioning machine? But I do know pretty much right away the probability that an arbitrary widget came from a properly functioning machine, and I do know right away the probability that a widget is bad given that it came from a properly functioning machine. Those are given in the problem statement. So in this case, I choose this way of splitting it up. In a different case where I was given different information, maybe I choose the other way. Okay. Another way to kind of look at this is the second way splits based on the functionality of the machine and then on good or bad widget. Like up here, I could imagine that I had instead split it on good or bad widget. So I could take all of my widgets and separate them into good ones versus bad ones. And then of the good ones, at least in theory, I could split those into ones that came from a properly functioning machine versus ones that came from a malfunctioning machine. And the same for the bad widgets. So it's a question of on which criterion do I split first and then second? In this case, it makes more sense to do it this way based on the information we're given, and this doesn't get us very far. In another case, maybe in another situation, another problem, maybe it makes sense to split the other way first and then second. So what if we have an example with cards? So probability of drawing a heart, then a spade. If we have a standard deck of 52 cards, 13 of those cards are hearts. So the probability that I draw a heart is 13 out of 52. But if I'm talking about drawing a heart, then a spade, and here I'm talking about without replacement. So I have a deck of cards, 52 cards. I draw one. To get a heart, then a spade, I need to get a heart on the first draw. And then to stay in the event, given that I got a heart on the first draw, I have to get a spade on the second draw. So when I draw a heart in the first draw, that happens 13 out of 52 times because there are 13 hearts in the deck, 52 total cards in the deck. After I've drawn a heart successfully on the first draw, there's still 13 spades in the deck. Because my first draw was a heart, still 13 spades in the deck. But now the number of cards left in the deck has changed. There's only 51 cards in the deck. So we might be tempted to write 13 out of 52 times 13 out of 52, but we have to be careful. The number of total cards in the deck has changed because I drew a card on the first draw. So given that I drew a heart in the first draw, the probability of drawing a spade on the second draw, when everything's done without replacement, is 13 out of 51 because there are 13 spades still left. All the spades are still left in the deck, but there's only 51 cards left in the deck. So 13 out of 51 and times 13 out of 52 gives me about 6.4%. Now, naively, we might think that this is the same probability as, say, drawing two hearts in a row, again, without replacement. But if we go through carefully, probability of drawing two hearts in a row, in other words, heart on draw one and heart on draw two, without replacement. So we're not drawing a card, looking at it, shuffling it back in. Well, that's probability of drawing a heart in the first draw is 13 out of 52, just like before. But now what's the probability of drawing a heart in the second draw, given that we got a heart in the first? Well, if we got a heart in the first draw and kept it in our hand, there's only 12 hearts left in the deck. The deck has now been reduced to 51 cards. So we have 13 out of 52 times 12 out of 51, just under 6%. So it is a different number, whether we're talking about drawing a heart, then a heart, or drawing a heart, then a spade. This has a bit of the kind of feel of like rolling dice, right? Like getting a one, then a one versus a two, then a three versus a three, then a two. When we have, a kind of a then versus an and, there's a counting issue there that we got to be aware of. This has a little bit of that feel. And then for the last problem in this section, there's a little application problem at the end of this slideshow, but I'm not going to go through that just to save a little bit of time. But last problem for this section, we'll consider a game show. This is, I guess, not a super exciting game show, but the way the game show works is we walk up, we roll a six-sided die. If we roll a one or a two, we walk over to box one and we draw a card from box one. If we roll a 3 through 6 on the die, we draw a card from box 2. And box 1 has 60% good cards, 40% bad cards. So 60% of the cards in box 1 are winners. And in box 2, 10% of the cards are winners and 90% are losers. So if we had our choice, we'd choose to go to box 1, but it's really the die that is sending us to box 1 or box 2. And we want to know the overall probability of winning the game of getting a good card. And so again, we can think, what way should I split this up? I see that there are two things going on here. We either get sent to box 1 or box 2, and then we either get a good or a bad card. Now I want to know the overall probability of getting a good card. And again, if I split up as like good card versus bad card, and then box 1 versus box 2, I don't think this is right for a couple reasons. One is this is what I'm looking for, but it's kind of buried in the middle of my structure here. And the other thing is that this just doesn't really work naturally with how this problem setup works, right? We get sent to box 1 or box 2, then we draw a card. So I don't think I want to go this way. I think I want to first split on whether I get sent to box 1 or box 2, and then whether I get a good or a bad card. And I see there are two ways to get a good card, obviously mutually exclusive. I can't simultaneously get sent to box 1 and box 2. So we have a very similar setup to our widget problem. And this structure that I kind of drew up above and again down here is sometimes called a tree diagram. This is kind of the analog of a Venn diagram. Venn diagrams helped us out with addition rule kind of ideas, and tree diagrams help us out with multiplication rule type of ideas. And the idea of a tree diagram is that let me zoom this in a little bit. So we set up our structure like this, and it's called a tree diagram because it looks maybe a little bit like a tree, like we have a root here, and then we branch until we get to kind of our leaves at the rightmost endpoint. And the idea being we get sent to box 1 or box 2 with different probabilities. Probability 1/3 and 2/3. We get sent to box 1 for 2 out of 6 possible rolls, all equally likely, or 1/3 of the time, and then box 2, 2/3 of the time. And then given that we got sent to box 1, what's the probability that we win? What's the probability we get money? 60%. And what's the probability that we lose the game? 40%, given that we got sent to box 1. And then given that we got sent to box 2, what's the probability of getting a good card or winning? Is 10% and 90%. And if I want to find, say, the probability that I get a good card from box 1, or in other words, the probability that I get sent to box 1 and draw a good card, given that I got sent to box 1, I just start at my root here and traverse the tree. Oh. And each time I cross a probability, I just multiply by it. So in other words, on 20% of my plays of this game, I'll get a good card from box 1. And then similarly, good card from box 2. As I traverse the branches necessary to get over to this good card, I see I get 2/3 times 10% is about 6.7%. So on about 6.7% of plays of this game, I'll get a good card from box 2. What's my overall probability of getting a good card? That's either good card from box 1 or good card from box 2. Clearly mutually exclusive. We can't get sent to box 1 and box 2 at the same time. So we just add these together with our addition rule. Total probability of getting a good card is 26.7%. So just over a quarter of the time that we play this game, we'll get a good card, we'll win the money. And right around 3/4 of the time we would lose. And here's the algebraic approach. We see we get, just using the multiplication rule, this 20% number. And just using the multiplication rule, we get the 6.7% number, and we add them to get 26.7%. So we can use this picture to kind of help us sort out the conditional probabilities and so on. The big thing to realize or to remember is that these later branches have conditions. The 60% is probability of getting a good card given you got sent to box 1. Are there any questions on the multiplication rule?
Yeah, so actually the only part that I didn't get was, so how is it that 10% of getting a good card from box 2? How is it 10%?
Oh, that was just in the problem statement. Yeah. Yeah, so
Oh,
we're just, yeah, we didn't calculate that. That's just kind of how the game is set up. Yeah, these 10% and 60%, those numbers are just given directly here. Yeah,
yeah,
good
and
question.
why I thought that the box 2 is 40% of getting good card, but I just got it mixed up. Okay, thank you. Now I got it.
Oh, yeah, no problem. Yeah. Any other questions? Okay. Oh, and one last little topic to wrap up the this PowerPoint and these couple of sections. Just discussing conditional probabilities a little more. One note is we're not going to cover Bayes' theorem in section 4.3. We're going to cover Bayes' theorem after chapter 5. I think it fits a little bit better there. So if we have our multiplication rule for dependent events, we can solve for the conditional probability by just dividing by probability of A. Assuming the probability of A is not 0, but we can get our conditional probability this way. If probability of A was 0, it would be a little, maybe not quite silly, but probably not very meaningful to talk about probability of B given A, because we are assuming that A has occurred, but if probability of A was 0, then it cannot have occurred. So we can derive a formula for the conditional probability in terms of other probability statements. Sometimes this is helpful. We're going to look at just kind of a toy example here. We'll actually skip over this one, but we'll look at this example just to wrap things up. So let's suppose that the probability of parking in a no parking zone and getting a parking ticket is 6%. I went to Pitt for grad school, so this was occasionally, you needed to park in somewhat questionable spots, and in the last, 10 or 15 years or so that I've occasionally driven through Oakland, they've gotten rid of a lot more parking spots. So it seems like it would be really tough to be a commuter these days on Pitt's campus. But if we have probability of parking in a no parking zone and getting a ticket is 6%. The probability you can't find a space and need to park in a no parking zone is 20%. And now the question is, given that you parked in a no parking zone today, find the probability that you'll get a ticket. In other words, find the probability of ticket given you parked in a no parking zone. Well, this is probability of no parking zone and ticket over probability of no parking zone, or that's 6% over 20%. 20% is 1/5, and that's in the bottom. So if I flip it up top, that's going to be 30%. So from a kind of so-called frequentist statistics point of view, from this kind of classical probability in a sense point of view, this is just a calculation we can do, and it just manipulates some of these probabilities. To give a little bit of a kind of, I don't know, a teaser for Bayes' theorem at the end of chapter 5, how somebody who adopts the kind of Bayesian philosophy might interpret this is something like this. That when you left the, say you go to Pitt or something, and these are numbers that relate to you. When you left the house this morning, you looked back at the last 100 days or something, and you said, okay, of the last 100 days that I went to school, on 6 of those days, I had to park in a no parking zone and I got a ticket. You also look back and you saw that, well, on 20 of those last 100 days, I had to park in a no parking zone. So now looking forward, you leave the house today and you say, okay, based on nothing else, based on not knowing anything else, when I walk out the door this morning, I think there's a 6% chance I'll get a ticket today. But then you actually get to campus and you say, oh, geez, there's some big event going on. I can't really find any good parking spots. I have a new piece of information that enters the scene that I have to park in a no parking zone, or maybe that I chose to park in a no parking zone. I suppose you don't have to. You can drive home or, park a mile away and walk, but chose to park in a no parking zone today. What's my updated probability of getting a ticket on the basis of some new information? My probability of getting a ticket has increased from 6% when I walked out the door this morning to 30% on the condition that I know that I've parked in a no parking zone. That's another way to think about this. That's a very kind of Bayesian philosophy way to think about it. The frequentist philosophy kind of way to think about it just says, oh, well, this is just a calculation we can do to figure out what this conditional probability is on the basis of some other information. And then, like I said, this last example I'll not work through just because it does take some time and we're running a little short on time. So just give me a minute here to get my screens and things set up. I'll be right back. Okay, so that wrapped up the bit of part 3, or sorry, 4.3 that we're going to talk about. So that wraps up chapter 4, part 2, PowerPoint. And now we're moving on to chapter 4, part 3. And get myself a little more room over here. The computer is also deciding to run really slow today. So tried to shut down a bunch of stuff before class, so I probably should have just restarted the computer. But here's the start of the last section in chapter 4, dealing with counting. So it might seem a little strange to have a whole section talking about counting. And number one, we need to know how to count things, because we have things like events, we have things like sample spaces. And in each of these, it's important to know the number of outcomes. Now, the events and sample spaces we've dealt with to this point have numbers of outcomes that are pretty easy to count. We roll a die, there's 6 different options, that's 6 outcomes. We might roll 2 dice, and that was a little bit more complicated. We had to make a 6x6 grid, but we pretty quickly figured out that there were 36 options for the roll of 2 dice, or 6 cubed for 3 dice, or similar idea for coin flips. But we could imagine more complicated events or sample spaces where it might be harder to count the number of outcomes than that. So there's actually a whole field of math that deals with counting. It's called combinatorics, and it's not always trivial to count the number of things that fit some criterion or something like that. So it's important for us to be able to count things, and it's not always trivial for us to be able to count things, as we saw with even something as simple as 2 or 3 die rolls or a couple of coin flips. So that's what section 4.4 deals with. To start section 4.4, we have the most basic rule, the fundamental counting rule. And it goes like this. Suppose that we have a probability experiment. It consists of n ordered trials. So I know, if I'm rolling a die, I know which roll was the first die roll and which one's the second die roll, and so on. If there's not a natural ordering like that, I might impose an ordering. Each of which has k sub I possible distinct outcomes. So I might have 10 different dice that are, say, different colors, and that maybe have different amounts of sides on each die, and I roll the first die, and that's a 6-sided die. It has 6 different outcomes. Maybe I roll the second die, it's a blue die, and it has 10 different sides to it, so 10 different outcomes there, and so on. Then the total number of unique sequences of outcomes is the product of the different outcomes for the different dice. So for instance, how many possible outcomes, how many possible unique sequences are there for 4 flips of a coin? So here we have 4 slots to fill in. For the first slot, I could fill it in with a heads or a tails. The same with the second, same with the third and the fourth. So I have 4 slots and 2 choices for each of the 4 slots. Now, importantly, we're talking about sequences of events here. We're talking about ordering or order mattering. So in other words, heads, heads, tails, tails is a different outcome than tails, tails, heads, heads. Getting the 2 heads first instead of last, we don't count that the same. It's not just, quote, 2 heads. It's heads, heads, tails, tails, or tails, tails, heads, heads, or heads, tails, heads, tails. Those are all different outcomes. They're different sequences. So what's the number of total outcomes? Well, we have 4 different slots, or 4 different probability experiments that we're running. So the number of outcomes is the product of the number of outcomes in each of the experiments. 2 times 2 times 2 times 2, or 2 to the fourth. In this case, 16. For a situation like this, we can actually enumerate all the outcomes. So let's actually write them out. The sample space, what would it be? Well, we have heads, 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 4 heads. We have 4 different ways to get 3 heads. If we get 3 heads, that means we get exactly 1 tail, and the tail can be in the last place, second to last place, second place, or first place. To get exactly 2 heads and 2 tails, we see there are 6 ways to do that. It's a little harder to count these, but if we go through systematically, we can put one of the 2 heads in the first place. And that gives us 3 choices for the second head. If we lock that first head in the first place, the other head can be in the second, third, or fourth place. Second, third, or now we have to skip one in fourth place. And then if we have tails in the first place, heads in the second place, we could have heads in the third, or heads in the fourth, or we could have heads in the third and fourth places. So those are our 6 options for 2 heads and 2 tails. We have 4 options for getting exactly 1 head. The head could be in the first, second, third, or fourth place. And then we have 1 option for 0 heads, getting all tails. Is there a question? I heard something, but I can't. If you have a question, can you pop it in chat? I couldn't exactly hear what you were saying. Okay. So we can't actually write out all the outcomes in this case because there aren't too many of them. But in most cases, we're going to have 1,000 or something like that outcomes, and we're not going to be able to write them out. So we could enumerate them like this in this case. And sometimes we're in a situation where we can do that and kind of double check ourselves, but not always. So let's look at Pennsylvania license plates, just your standard Pennsylvania. Does anybody have a question? Okay. All right. I think they muted themselves. Yeah. If you have a question. All right. Somebody keeps muting and unmuting themselves. So if you can either stay muted, or if you have a question, you can unmute and then ask or pop it in the chat. Okay. So standard Pennsylvania plate has 3 letters followed by 4 numbers. And note that, again, the order matters. So for instance, A, B, C, 1, 2, 3, 4 is a different plate than like CBA 4, 3, 2, 1. These are different results. So we can tell which one is the first character, which one's the first letter, the second letter, the third letter, first, second, third, or fourth number. So we have we have 7 slots to fill in with characters. The first slot has to be a letter, so it has 26 options. The second and third also have to be letters. And then each of the next 4 have to be numbers, so 0 through 9 or 10 choices for each of those. So what's the total number of unique license plates? Again, that's just the product of these 7 numbers, or it's 26 cubed times 10 to the 4th. And if we want to do that on the calculator, we have 26. We have an exponent button just above the divided by symbol, this caret symbol. 26 to the third power times 10 to the fourth power. Or that gives me 175,760,000. So probably enough plates to satisfy the needs for, for Pennsylvania. Yeah, could we get away with 3 letters and 3 numbers? Well, maybe, 17 million plates, but we might be getting a little bit close then, right? If I think there's something like maybe 10-ish million people in Pennsylvania, that might be cutting it a little bit close if we don't want to reuse plates, or we think that people might have plates on cars that or assigned to cars that they don't really drive too much. So this seems like a pretty good number of characters that also gives us some margin. So if we're thinking of, say, computer passwords, that would be another example. How many passwords are there consisting of 8 lowercase letters? So here again, we have 8 slots to fill in with characters, and each one has 26 choices. So our number of passwords is 26 to the 8th, or that turns out to be about 2 times 10 to the 11th. So something you'll notice on the calculator is we get this 2.08 and a whole bunch of stuff. And then we get E11. So E11, the E is for exponent. And so it's 2.08 times 10 to the power 11. So the E kind of means multiply by 10 to the following power. So 10 to the 9th is a billion, and 10 to the 12th is a trillion. So this would be if we move this decimal over 2 and then take 2 off of the 11. So this would be 208 billion different passwords. Now, if you're trying to keep, just your brother or sister or something out of your computer, that's going to be plenty. If you're trying to keep another computer out of your computer, where the computer can try passwords and enter them in and try them really, really quickly, it's probably not going to take it very long to get through 2 billion passwords and just kind of brute force its way in. So maybe we want a larger password space, a larger so-called password entropy. We want a larger search space for, say, a computer attacker to have to search through to actually find your password by brute force. One way we could do that is we could say, well, let's still have a password of 8 characters, but for each character, you can choose lowercase letters or numbers, or uppercase letter, or any special characters. So lowercase letters, uppercase letters, numbers, and then 10 special characters. There are 72 now different choices for each slot. So what does this increase my password space up to? Instead of 26 to the 8th, I have 72 to the 8th, or that's about 7 times 10 to the 14th. I get about 3 orders of magnitude. It's about 1,000 times as many possible passwords than I had before. That's certainly an improvement. Could we do any better than that? Well, something I might notice is that by increasing the number of characters available per slot, that increases the base. So what I'm doing when I'm changing the base, I'm looking at a function like x to the 8th power, and I'm changing x. That's a polynomial relationship. But I might know from, say, Math 108 or from pre-calc or something like that, that
I have a Zoom class, but I have to be here because I have another class downstairs that starts right after this. That's
All
all.
right, folks, if you can all stay muted, unless you have a question about the class. I think there are a couple people unmuting themselves and getting some background noise. So obviously, if you have a question, definitely unmute yourself and ask, but just to keep the background noise out. But okay, so we see that in this case, increasing the number of characters per slot, we have a polynomial relationship. 26 to the 8th turns into 72 to the 8th power. But exponential relationships, we might know, grow a lot faster than polynomial relationships. Can I increase the power instead? What happens if I increase the power, or what scenario would increase the power? That means making my password longer. So what if I just went up to, say, a 10-digit password? And there are some other reasons they use 8-digit passwords, like things like bytes and things, are in units of 8. So that has a little bit to do with it. And actually, in the old days, they would actually just truncate the password at 8. You can make a 15-character password, and they would just use the first 8. So a little bit like if you dial a phone number or something, and once you put in the 10 digits, it's going to go. Doesn't matter what you hit after that. But they don't do that these days. But what if we made instead of adding characters, what if we made our password 2 characters longer? Instead of saying you can choose lowercase, uppercase, numbers, or symbols, what if I said just lowercase letters, but 10 characters long instead of 8? Well, here we again get about 10 to the 14th. So by increasing our password length by 2 characters, we change that exponent. That does roughly the same thing as, what would that be, about roughly tripling the number of characters per slot for an 8-character password. So that's one of the reasons why you'll see that passwords these days are leaning more towards things like passphrases, where you just have a really long, 14-character long password or something like that. It's just a lot more robust to attack. There are some other reasons to go to that too, that have to do with like the ability to easily guess your password and things like, if somebody's password is just PASSWRD, that's a pretty easy one to guess. So there are some other reasons to go to passphrases, but we can see that changing the exponent, changing the number of things that in our sequence, has a much larger effect typically than changing the number of options per slot in the sequence. Sorry, my allergies are just like going haywire these days with this crazy early spring or something. And then here's an example from biology that I think is just really kind of crazy. Is if you think of the human genome, our genetic material in each and every one of our cells, in each nucleus in each cell, we have something like 10 trillion cells. Say in roughly each cell. Some cells don't have nuclei, but of the ones that do, we have this genetic structure that is a double helix that if you unwind it, it looks like a ladder. Each one of these guys is a base pair. So maybe this is like AT, TA, CG, etc. And there are about 3 times 10 to the 9th bases, or base pairs, I suppose. So our DNA, if we took all of our chromosomes and just lined them up back to back, so to speak, we'd have about 3 billion bases in our genetic code. Not all of it, maybe something like 1 or 2% of it codes for proteins, at least in a way that we kind of understand how it works anyway. But still, that's a lot of information that is stored in each and every one of our something like 10 trillion cells, more or less each and every one. So if each of these bases, if each slot on, say, the coding strand, once I determine what one side is, that says what the other side is. A T has to match with an A C has to match with a G. If they don't, that's kind of a big problem. So typically they will match. We have 3 times 10 to the 9th slots. We have 3 billion slots that we can line up to, choose A, C, T, or G in each one of them. So what's the number of possible human-sized genomes? Well, it's 4. It's the base here to the power 3 billion. Or this is like 10 to the billion. It's like a 1 with a billion zeros after it. I mean, I don't even know how many pages of zeros that would be in a textbook size book or something. It's, I mean, certainly larger than the biggest textbook that you have on your shelf. Just a 1 with all of those zeros after it is the number of possible human-sized genomes. Or if you think in terms of data, that's something like a gigabyte to 2 gigabytes of data stored. If you think of, the bytes being like 0, 1, or a bit, the bit map being like, if this was A, T, C, and G or something like that. So we'd have 2 bits per nucleotide base. And if you do the math, it's something like 1 to 2 gigabytes of data that's in each and every one of our cells. I think that's just really cool that we have like this storage device that stores a couple of gigabytes of data inside each and every one of our cells, and we have 10 trillion cells in our body. And when I say each and every one, don't go and complain to your biology professor. Some cells don't have nuclei in them, but more or less each and every cell. All right, so that's the fundamental counting rule. Are there any questions on that one? Oh, yeah, somebody raised their hand. Question.
Yeah, actually, I have a question because I was thinking about this and I was thinking back to the law of large numbers.
Yeah.
And, you gave that example about, this is a password, computer will eventually brute force its way through.
Mm-hmm.
But what if you have something intangible, right? Like, let's say, how does the law of large numbers apply to social things? Like, say you took UFO sightings, right?
Mm-hmm.
Is there any application that could be used?
Yeah, so that's a good question. One application I can kind of think of, and there's criticism, I don't know, there's debate on both sides of this, but one of the arguments of evolution is, well, yeah, sure, this thing was unlikely to have happened, say a whole bunch of little what are they, like tRNAs or something like that. Somehow that machinery just like hooked up together and like basically started life. Well, that was quite unlikely to happen. That's a pretty qualitative thing to think about. These certain molecules have to line a certain way and they have to come together this certain way to make a structure that can self-replicate. So, okay, that's pretty unlikely to happen. But if we have billions of years for it to happen, and we have, I don't know, trillions or quadrillions or some illion that's much larger than that number of particles, say on Earth or in the universe or something like that. If you have an extremely unlikely thing, but you have an extremely high number of opportunities for it to happen, maybe kind of on average, it happens a reasonable number of times. Or something like a UFO sighting, like in theory, somebody could say, okay, well, we can't really say that anything in this world is impossible. So it's not like impossible that aliens could exist or that UFOs could be around or something. but maybe we deem it fairly unlikely, or maybe you deem it likely, I don't know. But even if hypothetically, if we deem it fairly unlikely, if we wait a long time and there's a whole bunch of people in the world, can we argue that it's likely to happen? And that's the difficulty of those kind of arguments is you're taking a mathematical structure that couldn't care less. These are just logical rules. It couldn't care less about anything in the real world, right? We're just saying this is basically a thought experiment. In our minds, we're coming up with logic and we're coming up with assumptions and saying, based on these assumptions of how probability theory works and the logic that we choose to impose on that system, these are the results that we get. It's a little bit like playing a Monopoly game or something. It's like, these are the rules of Monopoly. And you're like, well, that's a dumb rule, or I don't like that rule. It's like, okay, I don't know what to tell you. Like, those are just the rules, you know? If we try to overlay the structure of probability on the real world to say something about UFO sightings or evolution or life or whatever it may be, something that's more qualitative, there's a lot of discussion and argument and philosophy that goes into that, right? That's not a trivial application to make. So, you know, for something like using probability to model, you know, die rolls at a craps table, the connection is probably much more obvious. Probably most people would be much more willing to accept the pretty much one-to-one transfer of probability model for the roll of a die to modeling what happens in the craps table and not really complain too much about it, right? For something like how do these probability structures apply to things like UFO sightings? That's much more slippery, right? So I think there's a lot more, you know, assumptions and a lot more matching up of how does this probability structure that we've created, this thought experiment, apply to the real world? Similar to like a Monopoly game, right? It's like, okay, if you are really good at Monopoly, does that mean you're really good at handling money in the real world? Maybe, maybe not, right? So like, what's the transfer? Or if you play Monopoly with your kids, does that make them more likely to be, you know, to understand financial things later on? I mean, I honestly don't know, but you know, that could easily be something that people debate about, you know, on Facebook and start calling each other names and spend a lot of time on. I don't know if that really answered your question or not, but
No, I think that was good. I guess I was just trying to get to the point, like, where does law of large numbers really apply to things where there's sentiment involved, or something was observed, but I can't, you know, I saw a ghost. I saw, you know, this witness did this.
Yeah, so I think the law of large numbers, it maybe is a little more about just saying that, you know, if there's, say, the probability of something happening is 1 in a million, if you do 1 million observations, you're probably going to see it about 1 time. Or if you do 10 million observations, you'll probably see it about 10 times. So I think that's more what the law of large numbers kind of says. It says that the distribution experienced in the real world empirically, in some sense, should match the distribution that we would expect from under probability theory. Now, the question is, how well does the model under probability theory model what's actually going on in the real world? So I think I think things like, does somebody believe that they saw a UFO when they actually didn't, is maybe more of a question of psychology, or I mean, you could even go as far as to say it's a question of philosophy. It's what is something even, what does it even mean to say that something's real or not real? You know, it's a little bit like the tree falling in the forest, right? If nobody is there to hear it, does the tree actually fall? If nobody's there to experience it, did the thing actually even happen? So I mean, there are deep philosophical questions, I think, and the more you investigate something like this, I think the muddier it becomes, at least for me anyway. The more that you know, think about the philosophy, or what does something like this actually mean to say that, yeah, this person actually saw a UFO, or even that, you know, you sat down at McDonald's and you actually ate a hamburger. What does that mean? Like, most people would argue one but not argue the other. So I don't know. It's that I think becomes a question that's outside of probability theory.
Thank you.
Yeah. So I don't know if that answers the question or not. Something interesting though that does come out of that is, you know, you look at say a set of passwords, or you flip a coin a whole bunch of times and you say this sequence of heads and tails, this sequence of if we flipped a coin 20 times, if we had 20 slots, we get 2 to the 20, or what would that be about? Well, 2 to the 10th is about 1,000, so this is about 1,000,000 different outcomes. If you actually sat down and flipped a coin 20 times, you'd get some sequence of heads and tails. Maybe you happen to get 10 heads, then 10 tails, just because it's easy for me to write. And you look at this and you say, wait, this outcome, 10 heads, then 10 tails, would happen about 1 in 1,000,000 times. Like, that's kind of crazy. I just did this coin flip sequence and I did it once and I happened to get a 1 in 1,000,000 event. Like, that seems very strange. Maybe I should go play the lottery or something. But if I flip the coin 20 times, I'm going to get some sequence. Nobody's going to argue that. I'm going to get some sequence of 20 heads and tails, and each individual sequence is a 1 in 1,000,000 event. So on a kind of big probability experiment like this, flipping a coin 20 times, the sequence that I end up with is going to be a rare sequence. So why would I think that it was like really creepy or a sign from God or a sign from the cosmos or whatever if I got 20 heads in a row on 20 flips? Or maybe I would think that my coin is like broken or something, like it cannot land heads or tails for some reason. Why would I look at this, and if I actually flipped a coin 20 times and got 20 heads in a row, I'd be like shocked or bewildered or whatever. But if I got heads, tails, heads, tail, some seemingly random sequence, I wouldn't care. Well, it's just because we ascribe meaning and interest to getting a bunch of heads in a row, and we don't ascribe meaning and interest to getting some sequence of heads and tails that's not a whole bunch of heads or a whole bunch of tails or something. That's basically the reason why. It's that we choose to ascribe meaning or interest or value or something to certain things and not to other things. So if I got 20 heads in a row, that's just as rare as getting this specific sequence of heads and tails, but I just don't recognize it as being interesting. Or another way to look at it is, if I was at the beginning of the coin flips, if I ask somebody, all right, what would be a cool sequence for you to get? A lot of people would probably say like 20 heads in a row. That would be kind of cool. So in a sense, we're like targeting that, even if we don't really explicitly say we're targeting it. Where not very many people would say, I think it would be really cool if I got heads, tails, tails, heads, tails, some seemingly arbitrary sequence of heads and tails. If I was targeting this for some specific reason, and then I flipped the coin 20 times and got it, I'd probably be just as surprised and happy as if I had gotten the 20 heads. So there's also that question of rare things happen all the time. We just ascribe meaning and interest to certain rare things. We see patterns more easily in certain rare things than in other rare things. So that's, I think, maybe another component to what's being discussed. But yeah, it's probability and stats, I think, is, when you really get down to it, it's as much a question of philosophy as it is mathematics. Because at some point we've got to take this crazy model that was just a thought experiment, bring it into the real world and answer questions on the basis of that model and make predictions on the basis of that model. And that's not an easy thing to do. Maybe that's even putting it lightly. It's quite a difficult thing to do, especially considering that most of the time we use words in a way that's very imprecise, right? We kind of get what we mean, but if you say, okay, you saw a UFO, what do you actually mean by that, right? Like, do you mean the literal definition of UFO, that I looked up and saw an object flying and I could not identify it? Well, that's not, strange at all. There's lots of things that I look up. I'm like, oh, what is that thing? You know, is that the space station, or is that a star, or is that just, you know, but saying, you know, in the context of an alien spacecraft, that would be a different context, or a flying object that it's likely that, you know, no human in a 10-mile radius could identify, or something like that, is different. So yeah, all of that stuff is that's kind of at the heart of why some people lean more towards the frequentist side of statistics, some more towards the Bayesian side. It's all these philosophical arguments about what we mean by probabilities and probability theory and so on when we interpret it in terms of the real world. But I think things like this, like the amount of data that's in each one of our cells, just kind of shows us, in a sense, how big the world is, even on this like microscopic scale that we just, you know, don't even fathom. Like if you know, wipe your hand down your arm or something, you probably knocked off enough cells that's like, you know, more data in there than is in your hard drive or something like that. So anyway, I digress. I get on tangents too easily. Okay, any other questions on the one question in chat? Okay, yeah. Yeah, exactly. So yeah, so Greg mentioned in the chat, and it's a question of, you know, what does it mean to say that something actually happened versus what I think happened versus what some other people believe happened? That's a deep question. If you really think about it, it's like, just because I would believe somebody more likely if they said they had a hamburger yesterday for lunch than if they said they saw an alien yesterday, you know, that's a question of how much of the likelihood that I ascribe to that event actually happening. And it's not easy to say what it means for something to actually happen. Yeah, so all good questions and points. Yeah, my wife and I actually, on our honeymoon, we went up to Maine, Bar Harbor, Maine, and I can't remember if it was the trip up or the trip back, we stopped in Portland, Maine, and there's I forget what it's called, but it's like it's a museum that talks about like, or that has displays of like cryptids and those kind of crazy things. It was just kind of a fun little excursion, you know. So they have like a display on the Yeti, and you know, the famous coelacanth, the fish that they thought was extinct for like forever, and then they found it at some point and it's not extinct. So I was like the National Cryptozoological Museum or something like that. Very grand name for kind of a small mom and pop kind of operation, but it was kind of cool though. So, all right, so the next topic that we're going to discuss builds, all of these topics build on this fundamental counting rule. That's why it's the fundamental rule. And we're going to look at a motivating example, the traveling salesman. So suppose that we have a traveling salesman. This is kind of back in the day when to sell something, you would physically travel to different locations. Yeah, definitely. Yeah, some cryptozoology is actually legitimate, and you know, some of it is quite a bit less scientific. So I think one of the issues today, or one of the difficulties today in many fields, you know, peer-reviewed journals not excluded, is we have so much information. We have to sort through the stuff that's relevant versus irrelevant, and that's reliable versus unreliable. Yeah, so the traveling salesman problem. So the idea here is we have a salesman that has to travel around. So this is back in the days when you would physically travel to a location to make a sales pitch. And the idea of the traveling salesman, is that they want to travel to 10 cities, specific cities. So, you know, we have my horrible rendering of the US here. And we have, say, 10 cities we want to travel to. And we want to know the number of itineraries. We would like to maybe minimize travel time or cost or something like that. So, you know, one itinerary might look like this. but there are a bunch of itineraries. I want to visit 10 cities. So I have 10 slots to fill. And I have 10 cities in a sense for each slot. But the thing that's a little different here is for my first slot, if I say, okay, well, what city would you like to start your itinerary with? I could pick any of the 10 cities. But once I pick a city, once I pick, Miami down here, I've used that one already. I've already visited Miami. I'm not going to go and visit Miami again on the next slot or, 5 stops down the road. I already visited that city. So once I pick a city for the first slot and I put it in there, I don't reuse it. I'm doing this without replacement. So if I pick Miami for the first stop on the itinerary, and then I say, okay, what's your next stop? Well, now I only have 9 cities left to pick from. And then once I pick the second stop on the itinerary down here, I don't know, Dallas or something, I say, okay, what's your third stop going to be? Well, now there's only 8 left to pick from. Until we get down to the last one, once we've kind of burned all of our cities. If I say, what's your last stop going to be? It's you only got 1 city left to pick. So here I have 10 slots. I have 10 cities to start with, but each time I use a city, I don't replace it. I kind of imagine that I have this like bag over here. With the names of 10 cities in it. And when I reach into the bag and pull out a city, write down its name, I throw that ticket out. I don't put it back in the bag. I don't replace that ticket to be potentially drawn again later on. I throw it out. Note that this is unlike, for instance, the where was it? For instance, the license plates. I could have A, 3333. That's a perfectly fine license plate. I could, if I use the character A, I don't, I'm not banned from using it another time. Of course, in 4 flips of a coin, I can certainly get multiple heads or multiple tails. I better be able to, or I won't be able to get 4 flips with only 2 choices. Or in the genome, right, I have lots of instances of the same nucleotide base appearing. But in something like this, though, so those were all with replacement. In a scenario like this is without replacement. And I see that I can come over to my calculator and I can do, 10 times 9 and so on, but that's going to take quite a while. I need to multiply all the numbers all the way down to 1. And certainly if I had 20 cities, that would be a lot of typing in. So I want to compute 10 times 9 times 8 all the way on to 3 times 2 times 1. And I am kind of suspecting that this is going to be a structure that I'm going to have to deal with on occasion, or maybe frequently enough that it warrants coming up with a little more notation for it. So I define a factorial. And I'll let you read the slide, but I define this as 10 exclamation point, where this exclamation point represents the idea of factorial. We would say that this is 10 factorial. So when I see an integer with the exclamation point after it, an integer factorial means multiply a positive integer factorial, means multiply that positive integer by all other positive integers that are less than it. So how do I get to that on my calculator? I'd like to write in 10 factorial, 10 exclamation point. And where that's located is in the math menu here. If you see math under like second alpha math under there, Going across the top, we have 4 different menus, and then in each menu, we have different options. So we have the math menu where we can like convert something to a fraction. We have the number menu where we can do things like find the absolute value of something. The complex menu for like imaginary numbers, things like that. And then the probability menu here on the right side. So we use this probability menu a good bit in this combinatoric section. And if you see number 4 here, option 4 is the factorial sign, the exclamation point. So I'm going to do second quit to get out of here. I'm going to type in 10 because that's the number I want to factorial. And then I'll enter my factorial sign. So I'll go to math. Here I'll just go left to wrap around to that probability menu. And I can either navigate down to 4 and then hit enter, or I can just hit the number 4 to select the 4th option. That gives me 10 factorial. So one more time, I'll type in 10 because that's the number I want to factorial. I'll go math. I'll go left to wrap around to the probability menu. And then I'll either just type 4 in order to enter that exclamation point, that factorial symbol, or I can navigate down and hit enter. That gives me 10 factorial. Then I just hit enter one more time. And there is my 3,628,800, 3.6 million or so. Oh, 3.6 million or so different itineraries. So if my salesman wanted to evaluate each one for some cost metric or distance metric or something and try to minimize over that, that's going to be a ton of work for a human to do, maybe feasible for a computer to do though. What if my salesman wanted to go to 20 cities? Well, 20 cities would have 20 factorial different itineraries. We're now at something like 10 to the 18th. I see this E18 at the end here. This is probably going to be out of really plausibility for even a computer to do. And for such simple objectives, having so many different itineraries, think of, say, something like FedEx, who delivers, I don't know, 10,000 packages in Pittsburgh every day or something. How many itineraries are there for 10,000 factorial? That's an absurd number. N factorial grows like n to the nth power. It grows faster than an exponential function. And we saw how fast exponential functions grow when we were talking about passwords. So there's actually a lot of really interesting computer science and logistics engineering and so on that go into solving such itinerary problems. And kind of interestingly, there's CMU Carnegie Mellon has this I don't know what you call it, like department, I suppose. It's not quite a department, but it's the Human Computer Interaction Institute. I went to a lecture there quite a while ago. This is probably old hat by now. But one of the things they were looking at is there are things that humans are good at and things that computers are good at. Computers are really good at just saying, find an itinerary, evaluate the cost, say the total distance, and then, remember that number, find another itinerary, evaluate the distance, ask, is that one shorter than the previous one? If it is, switch to the new one for the best so far, and so on. Computers can do that kind of stuff pretty well, just grinding through tons and tons of itineraries. And a human could look at this and say, well, if we want to just minimize distance, this maybe is a little bit silly. Maybe we could, maybe I could do something like this that would work a little better. So humans can look at just a picture like this and say, well, okay, maybe this area seems pretty efficient, but maybe this area could be made a little more efficient. So that was one of the things that that they were working on, was having kind of a table with a big flat screen where humans could look at these itineraries the computer has come up with, and humans could say like, okay, computer, don't, this area over here looks pretty good to me. It's probably pretty efficient. Don't focus on changing these, you know, these roots over here anymore, but this one over here looks pretty sloppy. You know, why don't you focus on, you know, these 10 points over here and try to find a sub itinerary that works better for those points and make the overall much better. So it was kind of interesting, like trying to combine the strengths of humans with the strengths of computers and kind of working together. But yeah, if you're interested in computer science or math or logistics engineering, any of that, you know, this is going to be a huge problem for, I mean, for FedEx, Amazon, UPS, any of them. Okay, so the so-called factorial rule is when we have n items to be allocated to n slots without replacement. Note also that order matters, just like before. So it's almost obvious here that order matters, but if I, you know, swapped these two, for instance, if I went from whatever, Miami to Dallas versus Dallas to Miami for my first two, that those are different itineraries. So we're looking for the sequence in order to be a different outcome. So when we have n items allocated to n slots where order matters and without replacement, the number of outcomes is n factorial. So building off of the traveling salesman, we have two more ideas, the lazy traveling salesman. So this salesman still has to physically go to all of the cities. And they were assigned 10 cities, but they're going to go to 6 cities and then, you know, hang out in Vegas or something when they should be going to the other 4. So this salesman has 6 slots to fill in, the 6 cities they're going to actually travel to. They have 10 cities for the first choice, 9 for the second. And let me actually write these out a little more thoroughly here. So there's 6 of them, 10, 9, 8, 7, 6, 5 choices for the last one. So for the lazy traveling salesman who's going to only visit 6 of the cities, but has 10 cities to choose from, what's their number of itineraries? It's this. Now, again, this is going to be kind of annoying to type into the calculator, especially if we had a longer string of numbers. If they had 20 cities to choose from and we're going to visit 12 of them, that's, you know, typing in 20 times 19 times for 12 numbers. But something I might realize here is that this is the start of a factorial. And see, if I multiply by 4 times 3 times 2 times 1, I end up with 10 factorial. But the thing is, if I just multiply by a whole bunch of numbers, I've changed the value. So if I want to multiply by those numbers and not change the value, I've got to divide by them too. So I've got to divide by 4 times 3 times 2 times 1 as well. But nicely enough, 4 times 3 times 2 times 1 itself is a factorial. This is 4 factorial. This is a little better to type in. I can go over to my calculator, do 10 factorial, remember 10 and then math, go to the left to navigate to the probability menu, and then 4 to enter the factorial symbol. And then I like to divide by 4 factorial. So I'll do 4 math to the left, and then option 4. And this gives me 151,000 200 different itineraries. This is a smaller number than the previous one, because what have I kind of done? I've kind of taken my my 10 cities in the bag. I've pulled out 6 of them and left 4 in the bag. The 6 that I pulled out have to be in order. So if I change the order, that makes a different itinerary. But the 4 that I've left in the bag, I've just left them in there, right? If I decided to not visit LA, Dallas, Miami, or Portland, Oregon, it doesn't matter whether I decided not to visit them in the order that I mentioned or in some different order. I'm just not visiting them. The order doesn't matter. For the ones I'm not visiting, but it does matter for the ones I am visiting. So there are different ways for me to pull out the 6. And then of each of those 6, there are different orderings. But I have a lower total number. It's not 10 million or 10 factorial 3.6 million or so anymore. It's down to 151,000. Because leaving the 4 in the bag, they can get jumbled up a bunch of different ways, and those all represent the same itinerary. And we have another notation for this. When I have n factorial over r factorial, I give this the notation NPR, and I call this a permutation. Or I have a mistake here over n minus r factorial. Get that n minus in there. N factorial over n minus r factorial is NPR. So for instance, up here, we had 10 items. We wanted to select 6 of them. And we're calling this a permutation because order does matter. So we're selecting 6 of the 10 items from the bag, putting them in an order where order does matter, where a different permutation, a different reordering counts as a different itinerary or a different outcome. So 10p6 is 10 factorial over 10 minus 6 factorial, or 10 factorial over 4 factorial. It should be the same as that number. So if we go to our calculator, if we navigate again to the probability menu, we see that there's an NPR here. And this NPR is a binary operation. So just like a plus or a minus or something, we put number, operator, number. So we do like 10 NPR 6 is how we enter this into the calculator, where that NPR is just its own symbol. So on my home screen, I type in 10. Then I navigate through the math menu to the probability menu down to NPR. And then 6. And this gives me the same 151,200. So we can get the number of itineraries either kind of by brute force like we did up here, or using this symbol. As a general rule, we always want to use this symbol. And the reason is that there are some instances where these factorials get really big really fast. There are some instances where if we try to evaluate the factorials on their own, like this one, then this one, it'll overflow the calculator. But the way that the permutation or combination we'll talk about later is computed inside the calculator is a little more efficient. It's a little smarter. And so there are some instances where this will overflow, but this will calculate just fine. So we want to use the NPR button, the operation in the calculator, if we can. Are there any questions so far? Okay. And then one last note is that this does generalize nicely. What is NPN? In other words, if I have N distinct items in a bag, I pull out all N of them and line them up in a certain order. That should just recover the factorial rule. NPN should be N factorial. So what is NPN? It's N factorial over N minus N factorial. That's N factorial over 0 factorial. And we define, for good reasons as well as convenient reasons, 0 factorial to be 1. So very important note is that 0 factorial equals 1. So this is N factorial over 1, or just N factorial. If I pull all N items out of the bag and then set them up in different itineraries, I should end up with N factorial different itineraries, and I do. So the permutation rule is a generalization of the factorial rule. Okay. And we come back next time, we'll talk about the lazy online salesman and the combination rule, and then we'll start into chapter 5. I would recommend pre-reading a little bit into chapter 5. It can be a little bit abstract, so having seen it once before we get to it in class could be helpful. Okay, I see there are a couple of questions in the chat. Yeah, so, yeah, the exclamation point, yep, that's the factorial. And that's also in that math probability menu. It's option 4 down here. Okay,